Hello, good morning, everybody. Thank you for having me again. I was here a couple of years ago, and I think I was in the exact same room, and I remember feeling a bit, covered over like that. So I'm sorry if I don't keep on looking up there. I still know you guys are there, and girls, and I appreciate you all spending your time with me here. I'm Monica Beckwith. I am a JVM performance engineer at Microsoft. My background is in OpenJDK, even before OpenJDK was born, mostly in the HotSpot JVM. So from, I guess, Java 1.42, I think that's when I started, and here I am. Today I want to talk about this trend towards concurrent collectors in OpenJDK. And I'm keeping my talk to OpenJDK because there are other JDK collectors out there. So you have the IBM J9 collectors, you have Azule's C4 collector. And I will draw similarities, especially from C4, because the upcoming collector, ZGC, does have some of the similarities in there. But I will not talk more about them in detail. The goal here is to have a groundwork, and I think that's the part of the agenda. So I'm going to lay a groundwork so when I use those terminologies later on about handshaking and stop the world, we are all on the same page with respect to global and thread local handshakes. I also want to talk about some similarities with respect to the way the heap is laid. For all these concurrent collectors, we have the heaps regionalized. So these are called regionalized collectors. So that's something that's common between all collectors. And then some other things like concepts, copying collectors. So I'm going to lay some concepts down. And how does collection happen? So the concept of collection set and how we choose the particular regions in a collection set. As time goes on, I will talk about the algorithms in these collectors and then similarities and differences, kind of give a comparison side by side. So let's start. So I want to start with the stop the world versus concurrent collectors. Even in stop the world, since JDK 9, I think, we have the concept of thread local handshakes. Thread local handshakes is nothing new. C4 had it for a while now. And the concept is something like this. So all your application threads, so this is the concept for thread local. So all the application threads are running. At one point, you have the GC save point here that's requested. And each thread, depending on the work they're doing, takes its own time to complete the work and come to a halt. At that point, there will be some GC handshakes that will happen. So this is if you want to look at your thread stack or something, that's where you hand that off to the garbage collector. And then the application threads can go on and do their work while the garbage collection threads are working. So this is the simplistic rendition of thread local handshakes. And then as the GC work completes, that's when you mark the complete phase of GC. Prior to the introduction of thread local handshakes, it was you will see the difference here. And as you get the save point request, your application threads take the time to halt. And that particular period is called time to save point. So if you listen to many of the people talk about this TTSB and how that may be an overhead for different collectors, that's what they're referring to. It's a time to save point. In global handshake, it's basically your most expensive halt. So the thread that took the longest to halt, that's basically the time to save point. And then your GC threads get to do their work. Remember, the application threads are still halted. Once the GC completes, then the application threads can resume. So this is a stop the world collector, and this is the time that it not only, so basically from the time the save point was requested to the time the GC completed, so that's the entire pause, so to speak. So even time to save point is counted as pausing time because the threads have to come to a halt. So with concurrent collectors, your application threads are still the same, and they'll keep on progressing till a threshold is reached. The concept of concurrent collectors is that you don't want to ever let it run out of heap space. So usually in stop-the-world collectors, you have something like the petal collector, where once you hit an allocation failure, and if it's generational, then promotion failure, then you start collecting the heap. So an allocation failure, so basically when the to space gets filled, that's when you cannot allocate anymore, that's when you start the collection. In concurrent collector, it's threshold based. So when you have a particular threshold in the old generation, if it's a generational collector, or just a particular threshold in the entire heap space, when you reach that, that's when you start doing your concurrent activities. So what that means is that I do not want to ever be in a condition that my GC doesn't get enough time to complete its work. The work of GC is not only marking, but actually moving live objects, okay? So in this particular case, we start with the concurrent activity, and usually you will see something called initial mark. And that's like a small stop-the-world pause. And the initial mark, and this could be thread local handshakes, or it could be the global stop-the-world. And that's when you identify the roots and start from there. That's called the initial marks. This activity of initial marking is done by GC threads, and it is stop the world, right? But global or thread local handshakes depends on the type of garbage collector you have. After that, the threads, the application threads, which we also call mutators, they resume, and the GC threads are also working in the background. This is the concept of concurrent collection, which means that the garbage collection threads work concurrently with your application. The thread count here and in the stop the world phases are different, because in the stop the world you can pretty much use most of the threads that are available to your application. In concurrent collection, when you are working concurrently with the application, you want to keep the garbage collection threads to a minimum, because you want to give most of the CPU time to your application threads. There's another concept that is kind of introduced with concurrent collection, and that's the application threads doing some of the job. So when the collector feels that there's too much pressure, or it depends on the algorithm. So if the object hits if the application thread hits the object that needs to be moved or marked, sometimes the collector will ask the application thread to go ahead and do the work. So it's kind of called sharing of garbage collection work, and that's more common in concurrent collectors. So you will find concurrent collectors to be not optimal in throughput, especially if you are not aware of these things, where the application threads are having to do some of the work. So I will show you numbers in the end, but just remember these concepts. So at the end of the concurrent phase, you have another stop the world phase pause, and that's called the remark. That's because you're working concurrently with two mutators. Now your object graph, live object graph, may have changed, so that's the time that you synchronize, so to speak, with all, and make sure that whatever you have captured and any new live objects that were identified as you were working, you are capturing everything, because it's all about correctness. GC threads will resume their work after the remark phase, and the application threads will also go on. So now moving on to the heap layout. So as with the introduction of G1 GC in OpenJDK, we have the concept of regionalized heap. So prior to G1, we all knew heap as this contiguous mass right here. And then with G1, we have this regionalized concept. So basically the same heap is divided into equal-sized regions. I think they range from 1 MB to 64, 32 MB, and it's power of 2. That's how the region size will change. Right now in G1 GC, for example, it's decided at when your JVM starts, based on your heap size requirements. In ZGC, it's adaptable. So now, the same concept of regions, but what if your garbage collectors were generationalized, right? So you have the young generation and the old generation. So the same region concept applies. So the young generation is a bunch of regions, basically, and the old generation is a bunch of regions as well. So currently, ZGC and Shenandoah are just single generation heaps, and G1 GC is young and old, has young and old generations. Then, so the next concept that I want to introduce is called the copying concept, and this is common for G1, for ZGC, for Shenandoah. The copying is either done in stop the world fashion or in concurrent fashion, but the concept is similar. You will also see the same concept in parallel GC as well, for example. So people also use the terms compacting collector and aka evacuation when they're talking about OpenJDK collectors. It kind of means the same thing. So you have the heap, and usually the heap, or if in a generational collector, that each generation will be in this form of from space and to space. Okay, so allocations happen into the form space, and then as you move or copy the live objects, they go into the to space. So as your from space starts getting filled due to allocations, there'll be a time that you cannot allocate anymore, and that's when you encounter an allocation failure. That's when you will have your collection start. Once, to be able to start collection, I was talking about the initial mark phase, that's when you identify your GC roots, which could be your static variables, your JNI handles, and your thread stack. And then you will, from those roots, you will start marking your live objects. So you'll try to trace the live object graph as such. So here we have identified these live objects that are highlighted. And then there are various other forms of collection. People call it sweeping. In this particular case, there's no need to sweep because we're just moving the live object into the to space, and then you can reclaim the from space. So as such, so you move from the from space to this to space. So all those live objects are moved, and then you can reclaim the from space. So at the end of collection, your to space is now the from space, and the from space becomes the to space. And now allocations will happen in the from space. Again, when from space gets filled, it'll move the live objects into the to space. So it's kind of back and forth, and that's how your objects age. The next concept I want to talk about is the concept of free regions and occupied regions. So for the same heap, even if it's generational or not, you have just a bunch of regions, right? And at any given time, I can represent the same thing as occupied or not occupied. So the highlighted regions here are occupied regions, and the other regions are not. The way we know about the free regions, or the not occupied regions, is by maintaining a list of them. So at any given time, we have a list of free regions. In case of generational collectors like G1, at any given time, these regions could be from the young generation, old generation, or even something known as humongous. And they don't have to be contiguous, except for humongous, and that's why they identify as such, because they could span more than a region. Now, the next commonality between all these collectors is the concept of collection set and how we collect them. Now, in order to be able to meet, or at least promise, or a soft guarantee of a pause time goal, we have to understand, the collector has to be in control of what it's collecting, or the amount of work it's doing. So to be able to control the amount of work, there's a concept of incremental collection. So at any given time, especially with the generational collector, you will not collect the entire old generation. You will only collect the least expensive ones. So that concept is called garbage first, and that's why the name of garbage first garbage collector. And now in ZGC and Shenandoah, you'll see similar concept of the least expensive region, collecting the least expensive region. So here is the same heap with regions that are filled, occupied, and the highlighted ones are the live ones. So we've already done the marking, and we have identified the live objects. And now we can reclaim the regions with dead objects. Many garbage collectors are smart, so they don't really wait for the actual copying phase or the moving phase to reclaim these spaces. So if a region is fully garbage, then it can be reclaimed during the marking phase itself. So for example, these two regions are reclaimed already. Then we go to the copying phase, and now we try to do something called the live object kind of accounting. So it's called liveness accounting. So we've tried to find out the ones that are the least expensive. So remember, the collector's work is to literally move objects from the from space to the to space, the live objects, right? So if I can move the least amount of objects, then my work gets done faster, right? So that's why the concept of identifying the least ones. So that's each collector has its own algorithm of identifying and having a collection set priority. And then the work of moving is simple as just moving from the identified regions into another region. So again, from the from space to the to space. And there, right, in this particular case, there were multiple from spaces. And that's usually what is called a collection set. So your collection set will be a set of regions that you have identified that as a part of moving from the from space to the to space. So again, as I mentioned, garbage first, that's the #1 priority. The candidate regions that we are using to move or to mark, in particular in cases of concurrent collection, you will also use the same concept to do marking or reclamation and relocation. And those are said to be the collection set. And as I mentioned, the threshold, so all these things, the threshold of incremental collection is not only pastime driven, but there's a concept of expensive regions. For example, in G1GC's case, there is the overhead of remembered sets, and which are basically accounting for incoming pointers, and the number of, if you have an expensive region because they had a lot of incoming pointers, then that becomes an expensive region overall. So it's not just the liveness, but also other expenses that could be, that would mean that you have to now update all the incoming references since you have moved the objects in the region. So these kind of accounting has to be taken into consideration when you decide your collection set priority. To be able to decide again for incremental collection, which is also known as partial compaction and or incremental compaction, you have different thresholds on the liveness of the region as well as the total heap. So if I can get away without doing any collection, I might as well do that. So if I have enough heap that I don't need to reclaim yet, or I don't think the reclaimable percentage is going to be enough, so I'm not, I'm not even going to bother with the collection. So you may see a lot of marking cycles without any reclamation cycles, which means that the garbage collector didn't think it was important to reclaim anything. Because again, copying and moving is the most expensive part of a garbage collection, or usually should be. If it's not, then your application is different. You gotta go and spend some time analyzing what's going on. So once a threshold is reached, then the GC stops, and that's simply what an incremental collection does. Now, let's talk about the algorithms, G1GC, Shenandoah, and ZGC. So the way I wanted to classify these collectors are based on the concepts that we mentioned. Regionalized or not, generational or not, compacting collectors. And then there are two different things that I wanted to highlight here because of the trend where the collectors are going. So with the introduction of G1GC, there was a concept of target pause time. Now, I think it was like 200 milliseconds is the default. So, and that was a soft real time, so to speak. So G1GC will do its best to meet the pause time goal, but it will not stop collecting if it exceeds the pause time goal. So that's what we see here. I will talk about what forwarding address and header means. I have some examples for that. And of course, G1 pretty much ticks all the boxes. I mentioned about the target pause time goal. There is a concurrent marking algorithm depending on how much time we have. It's called SATB, which is snapshot at the beginning. I have links, if we don't cover it in details, I have links where you can get more information on that. Shenandoah is an interesting collector. It's the same paper, or similar paper to G1GC, and it was started by Red Hat. That's the contribution to OpenJDK. And it started with the concept of Brooke-style indirection pointers, and I'll talk more about that, what that was, and how it changed back to now forwarding pointer as well, and what that means. Shenandoah's target pause time is supposedly 10 milliseconds, which means they target that their pause times will not exceed 10 milliseconds. And I think ZGC as well is the same concept. You will see, like I mentioned about Shenandoah and G1GC similarities. Again, the algorithm for concurrent marking is SATB, snapshot at the beginning. ZGC is a very different algorithm. They have the concept of colored pointers, and they do striped concurrent marking. And I'll talk more about that as we touch each of those collectors. So now go on to differences. So when we talk about concurrent marking, they are basically these sets of phases that you will see in all concurrent collectors. Because of the introduction of, like I said, the thread local handshakes, initial mark and remark may be really, really short pauses because it's just the handshake that is necessary. But much of the work that's done in the concurrent phase is still there. So I'm going to put this up here, and then we're going to go discuss more of the details. But and this will be the first time I'll dive in deeper because the concept, like I said, is similar. So once you do the initial marking, so you mark the objects directly reachable by routes, in G1GC, because it is regionalized, you have the survivor spaces that needs to be scanned as well. Because remember, from space to space. So for the young generation, the to space is the survivor space. And because we already moved objects, we need to make sure that we've identified routes or things that need to be scanned in there. So that's the extra phase in concurrent route region scanning because of the generational GC. The algorithm that is snapshot at the beginning will happen during the concurrent marking phase, and that's where you traverse the live object graph. And then there is a final marking and cleanup, which is also, final marking is also known as remark, and that's where you do these, there's some of the work of housekeeping that needs to be done. And during cleanup, you identify the liveness of each region and the expense of these regions. And you sort the regions based on liveness and expense. And then you can do a compaction. Compaction phase in G1GC is stop the world. And basically it's moving live objects from set to the two regions. So let's look quickly at snapshot at the beginning. The concept is that since it's a concurrent phase, we want to be able to take a snapshot of the heap as it were, right? And with that snapshot, we will have finger pointers to move up and down and say either implicitly mark live objects or explicitly mark it. So depending on how much time we have left, we either assume the regions that objects in this particular area are live, because I didn't get a chance to touch them right now, but since I can do it in my next cycle, I'm okay. And so all these regions below this finger are live, and I'm just gonna mark in this particular area. And so this way, a GC can guarantee that any objects that were live at the beginning are still live, even if that means that I have an overhead of floating garbage. Basically, if the object graph changed while I was marking them as live, and those objects are no longer as live, I will not go, the garbage collector will not go and go revisit them, because then it's like an endless loop right here. I'm just gonna move on, and I will not collect that. I'm just saying it's implicitly live. I'm not gonna collect that. So this is what I was saying. So because of the mutation, I am just gonna assume that it's implicitly live, right? So to be able to capture any reference updates, there is the concept of logging any new references that were updated while I'm doing my concurrent work. And that is why we need barriers. So G1GC does need barriers, and the logging in the log queue is enabled by a Prewrite barrier. There's of course a book right there that I've listed, and also see, that's Jfokus. So that's when I was here, 2017. I did a presentation at the Language Summit talking about write barriers in G1. So that's the link to that. So a little bit about pre-write barriers. So anything of this type of x.f equals y, we kind of guard it by if marking is active. That's kind of an optimization. And then you put the previous value, you store the previous value, and you want to check if that's null, not null, and then you enqueue that. So I saw that assignment, and I'm going to enqueue it, and that's simply the barrier, okay? So it notes all these kind of assignments, as long as I'm marking. So marking is concurrent, I see assignment, I enqueue it, because I need to touch that later. So then you go and do the work of enqueuing. And if the garbage collector cannot do it, then the work gets transferred to the application threads. There's also a Postwrite barrier in G1GC, and it's something similar to this particular object.field is equal to some other object. And since it's Postwrite, that's why it's called. It's very smart naming right there. And again, G1GC wants all garbage collectors have some optimization they want to do because they want to lower the overhead. So here, basically, if the check evaluates to 0, then you don't need the barrier. And if it's not 0, then it enqueues the card in the update lock buffer. Again, for more details, please look at the Jfokus talk as well as the book. Okay. Now this is the concept of forwarding pointers, and this is similar to anything that came before G1GC and G1GC itself, because we do stop the world compaction. So in parallel GC, in single threaded GC, CMS, whenever they did stop the world, like the full fallback collector, it has the same concept. So a Java object has a body, of course your own object, and then it has a header. The header basically is a pointer, so it's got 2 parts, pointer to an instance class, and then there's a mark word. The mark word is further divided into a pointer and a few bits. Okay? What the GC workers do, they compete to install a forwarding pointer right there. And if you go look at the source, hotspot source, you'll find that the instance class, whenever the pointer, it's an internal representation. It's an internal data structure for hotspot VM, and it's basically its own representation of Java classes. And the mark word is used for different things, and when you learn about value types, you will learn how why you cannot do certain things because of the mark word not being there. But usually, for other normal Java objects, you will see that locking and other information is stored in the mark word, and vice, or on the stack or whatever. So it's pushed and popped or whatever. But for our particular thing for garbage collector right now, when the mark bits are 1-1, then the workers will install the forwarding pointer. So instead of that pointer there, you will have the forwarding pointer installed. Okay. Now moving on to ZGC. So as you see this, it's similar. So you have the initial mark, concurrent mark, final mark. Now after that, it is not stop the world compaction, it's actually concurrent. So you prepare for compaction, you start compaction, and then you do the concurrent compaction. And the concept of compaction is the same, moving from region to region. And because it's done concurrently, then you have the concept of concurrent remap, which means you're trying to fix up all the pointers. Because remember, anytime you have incoming pointers, you need to update that because your location just got moved, right, from the from space to the to space. So you have to fix up all that. These are slides. This particular table was made with the help of the slides that Per did, a presentation that Per did at Jfokus again. So this is a popular conference for garbage collection. And the concept of concurrent marking is the colored pointers. So all these newer GCs, newer concurrent GCs, are geared towards larger heap and smaller response time, right? So the way ZGC achieves it is you divide this larger heap into logical stripes, okay? And each GC thread works on its own kind of local stripe, so that the interaction between these threads is minimum, right? Because, as I mentioned, that thread local handshakes was introduced in JDK 9, and that ZGC was the reason why they were introduced. So because you can do something like thread local handshaking, you literally have to just transfer state, and then you can go and resume your work. So these are your GC threads, and you stripe the region, the heap as such, and based on the number of threads that you have, you assign those stripes to each of those threads, and so on and so on. So all these threads will go and do their local work, and any kind of shared state is kept to a minimal. This is a very good concept of loaded reference barrier that is very important. This concept is explained very nicely in the C4 paper, the Azul C4 paper, and I'll have a link to that here. In its simplistic form, what loaded reference barrier is basically anytime you see a bad pointer, like a pointer that is not clean or that hasn't been moved or is in the moving phase, you make it a good pointer. And that's what a barrier is, basically. Any bad pointer, you change it to a good pointer. So, and this is where application threads can help. So that's the concept of self-healing. So anytime an application thread encounters a bad pointer, then it can help to make it a good pointer. So that's when the GC is transferring its work onto the application threads. Okay. The reason we can use this concept of loaded reference barrier is because the GC itself imposes two sets of invariants. So anything that's visible and it's a reference, the GC guarantees you that it'll be safely marked through. Okay? If it's not already done, then it's the GC's job to get it done. The second guarantee that it provides you, anything that at any given time, when you access a loaded, when the application thread accesses a loaded reference value, you will always have the safety of accessing the good reference, right? So if it's not good, then do the work, make it good, and then use that. So basically, those are the two guarantees that GC provides. This is the link to the paper for the continuously concurrent compacting collector, and it's very nicely described, the whole concept of loaded reference barrier. Here's an example. I'm going to just kind of quickly walk through this one and So basically, anytime you have a bad bit mask, you can go to the slow path of making it a good bit mask, okay? For example, here, in code, it'll look something simple as this. You have a reference update right there. You test if it's a bad color, and if it's a bad color, then please go ahead and make it the good color. Otherwise, just continue your path. So again, this is explained in that the slide deck from Pear. Now, the other thing that ZGC introduces is something called as colored pointers. So if you go to these objects and you look at the addressing space, you have all, if it's a 64-bit addressing space, so you have all 64 bits. In ZGC's case, from 0 to 41 is your actual object address, and then from 46 to the 63rd bit are your unused bits, which can be later on used for other things if wanted. But the object header will be able to identify A, if it's marked, and in what phase is it. So is it known to be marked? And then if it's in the relocation set, so is it remapped or not? So have we moved it or not? So all that thing is identified in the object address itself. So looking at the object, you can tell what phase is it and if it's finalizable or not. So that thing is already stored in the object head, in the address of the object. Okay. More details on that slide. So the idea of virtual address mapping or tagging is different, and it depends on the underlying architecture. So if your hardware supports it, the hardware like Spark and ARM64, when they support it, you can actually literally use the tagging bits. And if they don't, if the hardware doesn't support it, like x86, 64 doesn't support it, then you will do virtual address map, which is called, you'll do multi-map. So basically for all these, like marked 0, marked 1, remapped, you will have 3 different virtual address areas, and at any given time, the object is either in this one, or this one, and you kind of move back and sort of like move in the sense of virtual addressing. Concurrent compaction. So again, ZGC does do compaction, but it does it concurrently. And to be able to do that, I talked about the barrier, right? I mentioned about how the barrier is self-healing. And one advantage of ZGC is the off-heap forwarding tables. And C4 also has the same concept. And because you have something off-heap, you can immediately release and reuse the virtual and physical memory. So something that's off heap, that means you, as soon as the region is free, the area is free, you release, reuse. So it's really, really fast having off heap tables. Now going back to Shenandoah, I kept this last because of what you'll see. So when I talk about ZGC and Shenandoah, you have to know that they are not product garbage collectors, so they are experimental. Experimental means just what it means. As soon as they see something that needs to be improved, something needs to be added, it gets added. And then people go try it, and then they find bugs, and then say they report that back, and so on and so forth. So Shenandoah, I'm going to quickly go through it because I want to leave some time for questions. So it has the same concept as G1GC Snapshot at the beginning, so we already covered that. It has the Prewrite barriers again because of SATB. We covered that. And Shenandoah also, like in the past, a particular version of Shenandoah had read barriers, it had copying write barriers, and now, recently, both that read barrier and the copying write barrier have been superseded by the loaded reference barrier. Now, loaded reference barrier, remember, it's the same thing that I just covered for ZGC. So basically, Shenandoah adopted the same concept of loaded reference barrier. So want to learn more about it, go ahead and read the same paper that I said, the C4 paper. And quick recap of what that means. We have strong two-space invariant, utilize barriers as reference load, check if there's a fast path. If not, then go do the slow path. Okay? Shenandoah before all these cool updates had a concept of Brooke-style indirection pointer. Basically, for every object, you had an indirection pointer. So that's an overhead. So the forwarding pointer is placed before the object, and then you have to dereference each time. So every time you had to dereference. So that's an overhead. That is a penalty that you have to pay for using Brooke-style indirection pointer. So now that has been superseded, and they use similar concept to what I showed you about in G1 and any of its predecessors. So you have the body and the header. At any given time, you will only have, because of the two-space invariant, at any given time, you will only access the good copy. So remember, if you have a bad reference, you will only access the good one. So from the from space, you will install a forwarding pointer that points to the two-space object. So any given time, you will always be pointed to the correct copy. And that concept is detailed in that link, the blog link that I have linked over there. Now on to performance. What I'm going to show, and because that's one of the things, the reason I know all these things is because I want to learn about it so I can do a good fair-ish comparison, and that's where we started. So one thing I didn't mention, G1 GC is the default collector. So basically when you do out-of-box performance, you will get garbage first garbage collector since JDK 9, OpenJDK 9. And before that, you had the parallel GC collector. So here's a benchmark. It's SpecJBB, and only two things I've shown here are basically the full system capacity, which means it's in JBB, it's the concept of maximum injection rate, and the responsiveness, which it's called the critical JOPS. Basically, you have a response time percentile, I think 95th percentile, that you want to measure the injection rate at that. So what you see here is from runs 1 to 7, there's a lot of variability with parallel GC when you compare that to G1 GC, okay? And then I kind of build on the same concept. And then I wanted to see how it changes with LTS, how much of innovation is happening in G1 GC because of the introductions. You know, people always talk about when can we move to these other cool collectors? But, you know, people are not, since G1 GC is a default, there's still a lot of innovation that's happening. This is with the heap sizes right there. Again, in these graphs, higher is better because JBB, that's the whole concept. The best number gets the max, you know, it's kind of gets the fame. So here we see that responsiveness is getting continuously improved. I didn't want the other collectors to be left behind, so I wanted to see the improvements that happened in the other collectors. So from JDK 11 to TIP, here I'm only showing ZGC, G1, and of course I'm showing the parallel GC because I had that as a reference. But I'm not showing Shenandoah because Shenandoah only made it to JDK 13. It did not make it back yet into JDK 11 updates. So that's why you don't see that. So as you see, there is some sort of improvements happening every place. G1 GC sees the most improvement for responsiveness. But other collectors are not far behind. So there's always innovation is happening at the tip. So anytime you want to try an experimental collector for that matter, you should definitely look at the tip, and especially with Shenandoah, as you saw, lots of things have changed. So if you went back to the 13 version that was there, your performance may not be as good as the most latest one. And the final one, and I have 5 minutes left, so this is the final slide. Here, what I've shown is that I want to try to do a little bit of fairish comparison, like as I mentioned. With ZGC and Shenandoah, there's actually no tuning that's necessary except for the maximum heap size. With Parallel and G1, I did minimum tuning, which means that I gave them new size because they're generational collectors. I gave them a hint of what the new size should be. And as you can see, the maximum injection rate is really high with Parallel GC because that is the throughput collector, but G1 GC is not that far behind. Shenandoah and ZGC, because they are concurrent collectors, especially with the concurrent compaction, where the mutated threads have to do some of the work, they still struggle with the throughput part of the application, right? But they are really good, especially ZGC, is shining when it comes to the responsiveness at 95th percentile. So these are some quick comparisons that I did so that I can show you some numbers. Of course, this is going to change because innovation keeps happening at the tip. So your mileage may vary as soon as you leave this room. Further reading, please go and there are references at on each slides, but also there's some other cool discussions as well as some videos that you can watch, and everything is shared here. Z barrier, if you want to read more about that, go to that OpenJDK link. Again, that may change, but that's the file name if you ever have your own OpenJDK drop that you keep track of. Okay, that's all. Thank you all, and I'll take questions. Yes.
I have a question concerning parallel versus concurrent GC threads. When we had stop the world, as you said, you should maximize the number of parallel threads. But now when we have handshakes, how then should we tune the number of parallel threads? Or are there even parallel threads, so to speak?
There are still parallel threads, and that's a very good question. There is, if you remember the initial mark and the remark, that's always stop the world. Right? And the concept of parallel thread always applies to the stop the world phases. So anytime even with handshakes, the more so if you have application threads, they will come to a halt, and then the GC threads will come and try to get the information or the handshake, right? If you have equal amount of GC threads that are doing the work, your application threads may slow down, but they will not fully halt after the handshaking is done. So the concept still remains the same. By default, we'll still keep it at 5/8 or something like that of the total number of threads available, CPU threads available. So yeah. You had a question? Yes.
Yes. I get curious by detail. You mentioned that the mark word, if I did not misunderstand you, is not present on the value objects, the upcoming value objects, and therefore there are some restrictions on what GC can do about it.
Well, it's there's a little different. It's the header, the concept of header. So if you could identify immutability of the object, and I'm not going to go into details of that because I'm pretty sure lots of people have great talks on that. And so if you can identify the immutability of the object, then you do not need certain things as the header. And what happens, and you can do certain optimizations like allocating in stack for that matter. So they don't even need to be on the heap. Since they don't need to be on the heap, then you don't need that locking and all the other things that come with the overhead of being allocated on the heap. So it's kind of like an optimization from my perspective. There are other advantages, like I said, lots of people looking at Project Panama can give you a better idea of why they thought. But from a GC perspective, from an reducing allocation perspective, I think that's the advantage. So I have 1 minute left. I'll take maybe 2 more questions. Yes, go ahead.
Would running on a 32-bit system affect garbage collection negatively?
No, so one thing I did not mention about, oh yeah, sorry, I'm going to repeat the question. Will running on a 30-bit system impact a garbage collection negatively? It depends on the collector. So I think you mentioned that because you saw the ZGC and the object address. But in general, so ZGC is different, but garbage collectors were designed when we were on 32-bit collectors, right? So garbage collector worked with the first version of Java. So 32-bit is not a new concept. As we moved to 64-bit addressing, we did compressed oops and stuff like that. So those were optimizations. With ZGC, that's the compromise now. So it only works in 64-bit addressing spaces and stuff like that. So very good question. Thank you for bringing that up. We're out of time. You can always talk to me outside or reach out to me on Twitter or email. Thank you once again.